One.
This meeting is being live streamed. Okay.
Should we start? Hang on.
This meeting is being.
Yeah, start. Okay, good evening, everyone. We are very pleased to have our next speaker as A Smoot from Research Institute of Symbolic Computation at Johannes Kepler University in Austria. He'll be talking today on partitions, kernels, and localization. Over to you, Nicholas.
Thank you very much. And thanks to the organizers for letting me talk and for being patient with me. Here, I will very quickly share. Let's see. Do you see my slideshow?
Yes.
All right, good, good, good. And let me make it a bit bigger. Okay, maybe I'll push this down. Manipulating Zoom during a talk is always a little tricky, but there we go. I think you guys can see everything okay. Now I'm switching slides, so you're okay, right? All right, we'll start with the basics. I don't know who's in the audience who isn't familiar with the integer partitions. Is there anyone who actually isn't familiar with it? It's okay if you're not. Okay, so I expect most of the people in the audience are familiar with this. I give the definition of integer partitions and P of n right here. We've all seen this slide a lot. And I give the generator for P of n here. Okay, and the first few elements of the sequence of P of n, the partition numbers. And of course, this function has been studied for hundreds of years, since at least Euler. I'm actually told Gregory Leibniz studied it much earlier still. And it's really interesting that the very simple arithmetic properties that I'm giving you right here were never noticed. Maybe it's understandable the larger ones weren't noticed, but P of 5n plus 4 being divisible by 5 is a very simple and beautiful result. And Ramanujan, of course, was the first to discover it. Comparatively recently, about 100 years ago. And more generally, Ramanujan was able to discover this very deep and remarkable result, the foundation for everything else I'm going to be doing. That P of n is divisible by 5 to the alpha whenever n is the inverse of 24 mod 5 to the alpha. This is, again, given how pseudo-random P of n looks, this is remarkable. And the more general theorem I'm giving you here, that P of n is divisible by L to the beta, where L is the prime 5, 7, or 11, and beta is this result that you see here. Right? This little interesting wrinkle in the case that L is equal to 7. As we all know, Ramanujan missed that one little bit. Otherwise, his congruence families were absolutely correct. And very, very deep. And the thing is, now, a lot of you guys probably already know, if you look at this congruence family, when L is 5, or when L is 7, even with the strange wrinkle in the powers of 7, the proof is fairly straightforward. You can talk about it in terms of modular functions and Riemann surfaces, but you actually don't have to, because it turns out that machinery is subtle enough in these cases and the proof is simple enough that you don't have to worry too much. That's not true in the case when L is 11. 11 is a much more difficult one to prove. And the thing is, when you look at a large number of different arithmetic functions with similar generating functions to P of n, this kind of congruence family is very common. Or congruence families like this are very common. They're superficially very common, but they tend to vary wildly with respect to how difficult it is to prove them. So when I talk about a congruence family, I mean this sort of deal here. I'll define A of n to be the coefficient of q to the n in a generating function that looks something like this here, some product of q polynomials. Okay. Now, a congruence family for A of n modulo powers of some prime L is a set of divisibilities that looks like this here. A of n is divisible by L to the beta when n is the inverse of some fixed lambda mod L to the alpha. And as alpha goes to infinity, beta will go to infinity. That's what I usually mean by a congruence family. And generally, beta is either alpha itself or some relatively simple function of alpha. Maybe it grows at half of alpha. It might be the floor of alpha over 2 or something along those lines. Okay. Now, to give an example, so in the last couple of years, I've been developing certain techniques for proving infinite congruence families. As I say, it's influenced by for example, some work that Liquan Wang has done with Yifan Yang and a few other people. I'm trying to find a very simple general approach to trying to prove these congruence families. I'm trying to classify them and see how you can figure out which ones are really difficult to prove, which ones are really easy to prove, which ones require really advanced techniques and which ones don't. Because some of these are proved routinely in journals. Some are much, much more difficult. And I thought I would talk you through one that I have done as a result of collaboration with my colleague at Risk, Cusp Banerjee, and tell you to walk you through some of the ideas, how this relates to, because it's kind of in the middle. It's a difficult congruence family to prove, but it's not the most difficult. But we have a very nice procedure for proving it, and it reduces to the classical case for the easier congruence families. And it looks like we can extend it to the more difficult cases. In the more difficult cases, we don't have a very set, simple theoretical method for proving them. And I'm working on trying to extend my work so it will be provable. But so the example involves what are called K-elongated plane partitions of N. The generating function is on the screen right here. It's just a Q-Pochhammer quotient. dk of N counts the number of K-elongated plane partitions of N. This was studied by George Andrews and Peter Paula. So I give you like a length 1 K-elongated partition diagram, or at least a sketch of what it looks like. All right, it's a directed graph like this here. And the idea is each AJ is a non-negative integer. And if there's a directed edge from, say, AB to AC, well, that tells you AB is greater than or equal to AC. And what we're really interested in is the sum of the central nodes, in this case, A1 and A2K plus 2. Now, that's a length 1 diamond. An arbitrary K-elongated partition diamond will be a bunch of them hooked up together, like this here. And each of these diamonds has that complex structure that I just showed you, that's in each one of them. Okay. So dk of N counts the number of such directed graphs where the sum of the interior or the central nodes is N. Okay. Interesting enough, maybe I'll go back a bit here, just a moment. If you look back here, if I look at, say, D0, set K equal to 0, okay, the top will become 1 and the bottom just becomes your standard Q-Pochhammer for P of N. So D0 of N is P of N. So dk of N is a neat generalization of P of N. Okay, so it's already got some neat, there's some interesting motivations for studying it. A lot of this came out of work from Peter Paula and George Andrews studying McMahon's partition analysis and things like that. But it's also a very interesting generalization of P of N. And a lot of neat congruence families pop up as a result of this. Here's a good example. Now, this was proved by De Silva, Hirschhorn, and James Sellers, that the idea is you're looking at the arithmetic progression 5n plus 4, but you're also looking at, so dk, and k is changing in an arithmetic progression. So d 5j plus 5 of 5n plus 4 is divisible by 5. Note that in particular, let's set j equal to 0, d5 of 5n plus 4 is divisible by 5. And of course, if all this is set to 0, d0 of 5n plus 4, that's p of 5n plus 4. That's also divisible by 5. Okay. So this is a very, very pretty result. And this was, I should say, this was discovered by my colleague Kustov at Risk, who is absolutely brilliant when it comes to making conjectures like this and finding these sorts of patterns. When n is the inverse of 4 mod 5 to the alpha, then d5 of n is divisible by 5 to the floor alpha over 2 plus 1. This generalizes De Silva, Hirschhorn, and Sellers congruences, at least for a fixed k. Now, I should say, you can find congruences like this all over the place. Like the Silva Hirschhorn and Sellers paper describes a large number of similar congruences. And I think there's some more, there's a lot more congruences that have been found for decay of n. But congruence families like this are generally rare. They're a little bit harder to find. And in this case, they're a little harder to prove. This cannot be proved as easily as the proof, say, for P of n mod powers of 5. But it's not that bad. We have a procedure for proving it. It looked difficult maybe about a year ago. George Andrews and Peter Palla, they had been working on a few congruences, I think for D2 of n. Hang on. Give me a second. There's noise there. Peter Palla and George Andrews have been working on some congruences for, say, D2 of n, including a congruence family mod powers of 3. And it looks really difficult. But I just happen to be working on the techniques for proving these kinds of congruence families. And once you learn one or two tricks, they're not that hard to prove. And this is very similar. This is a congruence family that is more difficult to prove than for P of n, but it's not that much more difficult to prove once you learn the techniques. And the proof method, I think, is sufficiently interesting that it allows us to classify congruence families in general. So I want to walk through how to prove this congruence family, at least kind of quickly. So I'm going to skip over the general theory for the moment. We're not going to worry too much about this. Here's the big deal. Here's the theorem. Now, the way this usually works, okay, is that for each alpha, I can construct a generating function for d5 of n, where n is in the proper arithmetic progression. Okay, and that generating function can be rigged to be basically a modular function. And in particular, it's equivalent to a meromorphic function on a certain Riemann surface, the classical modular curve, in this case, x0 of 10. Okay. Now, the big deal goes like this. By looking at the topological properties of this modular curve, that can inform how complicated the proof is going to be of this congruence family. The genus is 0, so this is topologically equivalent to a sphere, okay, 0 handles. That means that each modular function corresponding to a case of this theorem can be written effectively in terms of a single special function, help module. Okay. The cusp count, that is, in sense, the number of punctures, the number of spots on the modular curve that all the rational points get sent to, is 4. Now, if it's equal to 2, then we have exactly the classical techniques available to us, the techniques used by Ramanujan, for example. But when there are more than 2 cusps, then there's complex behavior at the cusp, because these functions, in effect, they're modular functions. You can rig them so that they have a pole only at 1 or 2 spots. Well, when the cusp count is 4, it's hard to figure out where the cusps are, or where the poles are of these functions. Maybe I'll go back just a little bit and show you the basic idea. So I have some congruence family that looks like this here. Okay, A of n is divisible by L to the beta when n is the inverse of lambda mod L to the alpha. I construct a function L alpha, function sequence L alpha, okay, where each of these cases gives you, so say lambda alpha is the inverse of big lambda mod L to the alpha. Okay, so L to the alpha n plus lambda alpha gives you all the possible values of lambda n is 1 mod L to the alpha for a fixed alpha. Phi alpha is some prefactor that I rig in front to actually make it into a modular function. Okay, and again, being a modular function over gamma 0 n is equivalently being a meromorphic function on the classical modular curve. Now, the 2 key topological properties, as I say, are the genus and the cusp count. Right? And the big deal is, because this classical modular curve is compact, any function that is completely holomorphic on the entire surface, it has to be a constant. L alpha is not a constant, so it has to have a pole somewhere. Now, if I take, say, the set of modular functions, the pole only at a single cusp, say the cusp that the rational number 0 gets sent to, okay? and the genus is 0, then it turns out the set of all these functions with a pole only at the 0 cusp is just a polynomial ring. Cx for some function x, that's a help module. And I won't go into why this is true, but it's a very, very deep result. Now, if I'm working over, say, x0L and L is a prime, and the cusp count is, say, 2. Okay. Usually what that means is 0 and infinity will go to different cusps. Right? And we can represent each cusp like that. One is 0 and one is infinity. And my L alpha looks like this, I'll remind you. And if I rig it so C is positive, and phi alpha has order 0, so it doesn't have a power of Q at all, and that tells you that Q is like e to the 2 pi I tau. So as tau goes to I infinity, Q will go to 0. And because C is positive, it will in fact kill this entire function. In other words, L alpha will have positive order at the cusp infinity. And it's easy to show this is holomorphic everywhere else on the modular curve, equivalently for all tau in the upper half plane. So it has to have a pole at the cusp 0. So I can write L alpha as a polynomial in X. And you can probably expect very often I can write L alpha as an integer polynomial in X. And the coefficients of the powers of X will give me arithmetic information. That's how the standard proofs often go. And that's basically what now suppose n is not a prime. Excuse me. Suppose n is not a prime, then the cusp count is greater than 2. This is important. So when n is a prime, the cusp count is going to be exactly equal to 2. That can be proved fairly easily. When it's not prime, the cusp count is generally going to be greater than 2. What this means is this function L alpha will have positive order infinity because of the way the powers of Q are designed, but it may have poles at other cusps besides 0 because the cusp count is greater than 2. There are more cusps than just these two. So it's no longer necessarily possible to write L alpha as just a polynomial in X. But I can rig L alpha by multiplying by a function, say Z, that has positive order at every cusp except, say, 0. And a sufficiently high power of Z will kill all the poles of L alpha and push it into to CX. So L alpha will be in the localization ring of CX at S, and S is all your non-negative powers of Z. And if I choose Z and X properly, then I'll just end up with a rational polynomial expression in L alpha. This is the more general result you see. Instead of just being a polynomial and your help module, instead think of it as a rational polynomial, where there are heavy restrictions on what's going to be on the bottom of that rational polynomial. And this is when the genus is 0, the cusp count is equal to 2. The classical techniques of Ramanujan and Watson apply. When the cusp count is greater than 2, we use localization. We have rational polynomial expressions. When the genus is greater than 0, it actually looks like the same techniques will work just fine. I'm actually working on a few examples with my colleague at risk, Gustav, right now. It looks like the genus being greater than 0 can cause trouble, mostly in being because there's just a lot more work that has to be done. But it looks like you can use similar techniques. So we'll come back to that at a later point. So that brings us back to this theorem here. The associated Riemann surface is x0, 10. The cusp count's 4. And the genus is 0. The genus being 0 simplifies things a bit. The cusp count being 4 complicates things a bit. Okay. So I want to give an example. Here's the very first example of that theorem I just gave, that d5 of n is divisible by that power of 5 when n is the inverse of 4 mod 5 to the alpha. This is the first example of L alpha. First generating function is rigged to be a modular function. And again, it has poles at more than one spot. So that necessitates this 1 plus 5x to the 6th. This is that Z business. If I multiply L1 by 1 plus 5x to the 6th, that kills all the poles except for 1 and the pole at 0. And then I can write it as a polynomial on the help module, and the help module happens to be x. And if I add to this, the x is an integer power series, then okay, you can ignore the 1 plus 5x to the 6th. If you like multiply on the other side, all this, you'll notice all the coefficients are divisible by 5. So that means 5 has to divide 1 plus 5x to the 6th times L1, and 5 doesn't divide 1 plus 5x, so 5 has to divide L1. Of course, 5 doesn't divide this, so it has to divide 5, d5 5 plus 4, and that finishes the proof. Right? That's the first example. Now you'll notice this is a bit of a clunky example, a bit big, but the principle is still the same. We have a generating function, and now we can walk through a general proof by constructing a kind of induction argument. The neat thing to bear in mind here is that this is very similar to many proofs, except that L1 is no longer a polynomial, it's a rational polynomial. Right? But again, as long as you're careful what the bottom is allowed to look like, you can still extract the arithmetic information of interest. And again, this rational polynomial representation tells you a lot. Right? In fact, this whole thing tells you a lot. I only have one function being used, one variable, if you like, x. That tells you the genus is 0. I have a rational polynomial. That tells you that the Cusp count is greater than 2. So these representations, in addition to giving you arithmetic information, they're also relaying topological information about the underlying Riemann surface. Okay. So the general way to construct these generating functions, I'm giving it to you right now. You can think of L0 being 1. That may be useful at times. L alpha is going to have slightly different prefactors depending on whether alpha is even or odd. And I'm also going to have a variation in the power of q here, being 1 or 2. But otherwise, it's basically just a rigged generating function. These are modular functions over gamma 0, 10. And here's the main theorem. That if I take L to the alpha, I multiply by 1 plus 5x to the psi, and psi is this business you see here, and divide by 5 to the beta, and that's floor alpha over 2 plus 1. Right? Then I end up with a polynomial ring in the polynomial ring Zx. I haven't shown you what x is. It's a nice function, an eta quotient, a nice Haupt module. Exactly what it is isn't really important for us here. The big thing is it's a relatively nice function. And this gives us the divisibility of L alpha by 5 to the beta. So questions before I actually get into the proof. Like I'll walk through some of the details of the proof that I think are very important. But before I go any further, are there any questions? Okay. So here's the way we start writing a proof like this out. Again, I gave you L1. L1 is that relatively massive rational polynomial. It's basically what it looks like here. So the idea is I'm going to write each L alpha as a sum, say m greater than or equal to 1, of some integer valued discrete function s of m. It will eventually become 0 for m sufficiently large. This is a finite sum. Times 5 to a certain power. This will, in a sense, be my lower bound for the divisibility by powers of 5. And then times a bunch of rational polynomials that look like this, like rational monomials, if you like. Okay. So L alpha will look something like this. And hang on just a moment. I had to sneeze. But okay. L alpha has this form. And the idea is, so I can construct a sequence of U operators that should sound similar to anyone doing work in this subject. UI, U1 is just going to be the U5 operator, and U0 is just a modification of the U5 operator. And the idea is this is rigged so that if I apply U of alpha mod 2 to L alpha, I'll get L alpha plus 1. That's the basis of an induction argument that we're going to form. So we need to study how these U operators affect these rational polynomials. And I'm not giving you exactly what U0 is, but it doesn't matter too much. It's just a slight modification on U5. So there's a general relation for how these UIs affect these rational polynomials. It looks like this here. It's these nice rational polynomials. H, again, is discrete, and it has finite support with respect to R. And I've got these functions pi1 that will give you non-negative integers. Okay. And I'll give you what pi1 and pi0 are, for example. You don't need to memorize these, obviously, but I just want to emphasize that they are specific values that we can find without too much difficulty. Right. Now, here's the way the proof strategy is going to work. I construct a set of spaces, okay, and this again is very similar to the standard proofs, except in the standard proofs you just have polynomials like this, again with specially tailored powers of 5 here, but you wouldn't have this bit in front, this 1 over 1 plus 5x. Here you do, because again, rational polynomials. But the way we would start is I would define some spaces v and I to look something like this. And I can in fact figure out what the thetas are going to be. Theta 1 and theta 0, they're going to be slightly modified functions like this. Again, it's not going to do any good memorizing this, it's okay. But the idea is, I take L1 for example, and this should be a 6, excuse me. Because L1 was 1 over 1 plus 5x to the 6 times a bunch of stuff. So it should be a 6. But otherwise, you want to show that L1 is in V1 on top, but again, it's also divisible by 5. Okay, and we have that. The very first case gives that. The induction argument. If I take any f and v in 1, and I apply the u1 operator to it, I'm going to end up in v0. The bottom's going to go up to 5n, and I'm going to gain a power of 5. That's important. And then if f is in v in 0, and I apply the u0 operator, I end up in v5 plus 6, 1. Right? And that's enough. That would be enough if we could do this, right? Because then you have an induction argument, you go back and forth between these two sets. L alpha goes back and forth between these two sets, and every 2 steps it gains a power of 5. And that gives you what you want. So if I were to go to even to odd index, that's the easy one. Again, that would be u0 f is just in v5n plus 6, 1. I'm not gaining a power of 5. So that should be the easy one. Then if f is in v in 0, that means it has this form here. It's this rational polynomial. It's 5 to the theta 0, and that tells you it's in v in 0. And I apply the u0 operator to it. U0 is linear, and this is a finite sum, so I can just take it inside. I can pull out the SM and power of 5. And then I have that general relation for how the UIs affect rational polynomials, and I can expand all that out, and I can reorganize everything. And the big deal is I want this to be in v5 plus 6, 1. The 5 plus 6 comes from the way this U operator works. You don't have to worry about that. But to be in v in 1, this big power of 5 has to come out as being theta 1 of r. Again, theta 0 of m for x to the m. Now it's going to be theta 1 of r for x to the r. It's theta 1 because we're going to be in v in 1. And what that means is that theta 0 m plus pi 0 of mr has to be greater than or equal to theta 1 of r. And that's it. Just solve that inequality in your set. Similarly, going from odd to even index. So f is in v in 1. So f has this form. Again, it's 5 to the theta 1 of m times xm. Again, you don't have to worry about what theta is exactly. It's just the bookkeeping in this sense right now. M starts at 2 because of the way L alpha works when alpha is odd. I'm applying U1. Again, it's linear. So I can put this inside this finite sum and then pull these terms out and reorganize. Now I want to gain a power of 5. So it's not enough for 5 to all of this to be theta 0 of r, right? Because we're going to go into v0. We start in v1, we'll go to v0. We want this to be theta 0 r plus 1 because we want to gain a power of 5. Right? So we want theta 1m plus pi 1 mr to be greater than or equal to theta 0 r plus 1 for all r greater than or equal to 1. Okay, so this is what we're going to prove. Except for one thing, we're not going to prove it because the second was wrong. And this is the really problematic thing. And this is really astounding and tricky. When you try to prove things like this, the really strange thing, the first one does happen to work, but the second one doesn't work. This is not correct. Let me go through this again. F is in v in 1, sorry, it's supposed to be v in 1. And I apply the U1 operator. And again, I get all this stuff out. And I look specifically at when r is equal to 1. Okay, r is equal to 1, then I have x to the 1 over 1 plus 5x to the 5n. I want to look at the coefficient of this. And it turns out, r is greater than or equal to ceiling m over 5. That tells you that m has to go from 2 to 5 for the coefficient of x to the r, or x to the 1, excuse me. So it'll be s of m, h1 of m and r, and I got this power of 5 here. I didn't ask you to memorize this, that's okay, but you can just trust me on this, that theta 1m plus pi 1 of m1 doesn't give me any divisibility by 5 at all. This comes out 0. So the sum comes out like this. And each of these terms is supposed to give me a power of 5, and it doesn't. The coefficient, but in order for this to gain a power of 5, like the complete coefficient has to be divisible by 5. So there's only one logical solution. It's a brute force solution in a sense, but it's the only one that makes sense. All of this has to add to become divisible by 5. You don't gain divisible by 5 with each monomial. You have to combine them. Similarly, the coefficient of x squared over 1 plus 5x to the 5m has this form. And we do get 5 for the first couple of coefficients, but we don't elsewhere. It goes from m equals 2 to 8. And so starting with m equals 4, we don't get that power of 5 anymore. So we need to figure out how to deal with this. Now, there are a couple of ways of dealing with it. First of all, this sort of auxiliary function, h1 of mn2, we have a really, really nice result here. That hi of mnr is congruent to hi of m in minus 5r mod 5. That's very useful right away, okay? Because that means I can reduce, if I'm looking at what hi is doing mod 5, I can really just look at what congruence value n is mod 5 and just reduce it to that. So that's useful. With that, we can compute some very, very specific congruence values with relatively little work. For m equals 2, 3, or 5, I can derive this congruence. h1 of mn1 is just 1 mod 5. And I'm not going to, you don't have to memorize these, but just to say that we can get very, very specific congruences for these auxiliary functions. And with that in mind, when we plug all this in, you don't have to memorize. But again, if you're h1 of mn1, well, if I go back here, h1 of mn1 is just 1 mod 5. So that's just going to reduce this to s of m, s of 2 plus s of 3 plus 2s of 4 plus s5. I think it's s, let's see, when n is 4. Yeah, that's right. This is for m equals 2, 3, 5. So 4, it's 2 mod 5. So we have a 1, 1, 2, 1. So s2 plus s3 plus 2s4 plus s5 has to be divisible by 5. Right. If you have that, then the coefficient as a whole does have the divisibility of 5 you want. And if I give you L1, I pulled out the 5 here. And you can show that this coefficient plus 2 times this coefficient plus this coefficient is divisible by 5. In this case, it's very easy because these coefficients just drop off pretty quick. They don't, in general, drop off so nicely. But as you can see, 1 mod 5 plus 4 mod 5, it in fact works. Similarly, the coefficient of x squared over 1 plus 5x to the 5m is going to look like this here. So I have a 4, s4 plus s6 plus s7 plus s8. And that has to do, and I'm not going to show you this, but it does in fact come out divisible by 5. Of course it does, because you can compute L2, and L2 is bigger than L1, but it does in fact have the extra divisibility that you need. So we need to redefine these functions that the L alphas are in. Again, the odd indexed L alpha should be in here. The even indexed L alpha should be in here. Now, the n0 for the even indexed L alphas hasn't changed. It's exactly what I showed you earlier. The odd indexed L alphas have changed. It's not just that they're in here, but these coefficients Sm have to follow a certain collection of arithmetic properties. In particular, the vector Sm, as m goes from 2 to 8, you can actually make it arbitrarily large. Let's just say from 2 to 8, has to be in the kernel of this linear operator. And it is this that I think is really the core idea to think about. These rational polynomial representations come very naturally from the theory of Riemann surfaces, from the associated modular curves of the congruence family that pops up very naturally. But even if you try with these sorts of congruence families, it's often very difficult to manipulate them. This, I think, is the key missing piece. These SMs, the vector formed by S, if you like, has to be in the kernel of a certain linear operator. And depending on what congruence family you're looking at, what modular curve you're looking over, this linear operator may be very simple, it may be very complicated. For the classical cases, the mapping here is effectively the zero mapping. Everything is in the kernel. You don't have to worry about it. In cases like this, the kernel is more complicated. There are other more difficult congruence families where the kernel or where this operator exists, but it's much harder to write and represent. And that, I think, is how you can properly classify partition congruence families. You classify them by how difficult this linear operator is. In this case, it's not that bad. This gives you the first bit. So S2 plus S3 plus 2S4 plus S5 is divisible by 5. And then a similar one here. So that these two relationships on the SM are represented nicely with this linear operator. With this in mind, now the proof can work a bit better. See, it's not just enough. Because we just did that. I just showed you that, or I at least walk through the two counterexamples: x to the 1 over 1 plus 5x to the n, and x to the 2 over 1 plus 5x to the n. For all other x, you gain the power of 5 you need. This is just a little adjustment you need to make it work. But it's not just enough to show that, okay, if f is n, v in 1, I apply u1, and that should be a 0, excuse me. I end up in v in 0, and I gain the power of 5. That's not enough. I have to show that, okay, I'm in v in 0 with it, but I have to apply the u0 operator, and I got to be back in v in 1. In other words, when I apply u1 and apply u0, and I pull out that extra power of 5, what's left, the coefficients, the powers of x to the r, have to also be in the kernel of that linear operator. You have to have stability. So it introduces a new thing you have to prove, and that's not always easy to prove. So you have to prove stability. If you can prove this bit, you're set. Then the rest of the induction is easy. And I walk through, I've only been, how long have I been talking? It's not that long, right? How much time do I have?
At least another 20 minutes.
Yeah.
Okay, I hope I haven't gone too fast. I'm very sorry if I rush through this. But at least I won't take up too much time. I won't take up too much more time, okay? So the sketch goes like this. F is in V in 1. I want to show that 1 over 5 U0 composed U1 of F. Okay, it looks like this here. That's not that big a problem. 1 over 1 plus 5x to the 5n plus 6. And I've got this TW business, and TW is just constructed like all this. Basically, you apply U1, you apply U0, and you just collect everything. And it looks something like this here. This is double sum, this Sn, this H1, this H0, and then this lovely massive power of 5. Right? And you want to show, first of all, you want to show that T of W is an integer. That's not too hard to prove. Then you want to show that the vector by T is in the kernel of omega. And once you've shown that, you're set. And I want to walk through very, very quickly. Hang on a second. I just, what is this? Okay, this time. So I'm going to share my Mathematica screen. Just a moment. Okay, can you guys see the Mathematica notebook?
Yes, we can see it.
Excellent. Okay, so what I'm going to do is I'm going to construct that T of W function I just showed you. So there's a bit of computer algebra here, but it's not that much. So theta 1 and theta 0 are just the powers of 5 that we have to worry about. And I define the function T. I'm calling it T hat, but it's very similar to what we just saw. I have a double sum. I have Sm times H1 times H0 times 5 to that long power. Now notice, when we define T of W, I did H1 of M in R times H0 of R 5 in W. But again, H1 of M in R is divisible by, or is equivalent to H1 of M minus 5 R. And it turns out we're mostly interested when N is 1 mod 5. So I can reduce this mod 5 all the way down to this. And similarly, I'll bring more H0 of R5W. So that congruence is that reduction congruence is very, very useful. I can just work with H1 of N and H0 of 5. And I'm working mod 5, so we're okay. All right. Now, if I compute T of W, I want W going basically from 2 to 8, because that gives me the full set of TWs that I can check for the kernel. H2 is going to look like this here, and I'll actually go through it in real time to show you. H3, H4, H5, H6, H7, and H8. Now, you may worry, H2 is supposed to be an integer. It doesn't look like an integer. Yes, but don't forget, S2, S3, S4, S5, S6, S7, and S8 are in the kernel for that linear operator. We can use that to our advantage. So I go through H7, H8. Obviously, H4, H5, and H6 are integers, as long as the S functions are integers, which they are. But now I can take, for example, so again, I know that S2 plus S3 plus 2S4 plus S5 is divisible by 5, by hypothesis. It's only 4S4 plus S6 plus S7 plus 8. It's also divisible by 5. So I define this ideal, right? And now all I'll do is just check the numerators of TW are divisible by 5. So H2 is this. So I just multiply by 5 and just check what's left is divisible by 5. And then it will cancel the 5 out, obviously. So I just do polynomial reduction of HT2. I multiply by 5 to kill that denominator. And then I check and make sure that it's in the ideal. And the remainder is 0, which is exactly what we want. Mod 5, that is. And I can do the same thing for HT3. Right? And then 4, 5, and 6 were already integers. They didn't even need to be checked. But in these two cases, we can check as well. So see, it's large. It's a computational procedure in a sense that it's just really complicated. In principle, you could do this by hand if you wanted, right? But it's a relatively straightforward procedure. So that shows you that each of these is in fact an integer. Now we have to show that the vector TW, W goes from 2 to 8, is a member of the kernel, right? What does it mean to be a member of the kernel? Well, again, remember, for example, S2 plus S3 plus 2S4 plus S5 is 0 mod 5. So I'm going to show the same for T. T of 2 plus T of 3 plus 2T4 plus T5 is divisible by 5. How do we do that? Well, look at T2 plus T3 plus 2T4 plus T5. I expand that out. Takes a little moment because the computer has to do a quick computation. There it is. And then we reduce this mod that ideal. And the remainder comes out 0. So this goes to 0 mod 5, so long as the functions S are in the associated ideal. And then similarly, 4S4 plus S6 plus S7 plus S8 is divisible by 5. So what happens if I replace it with T? Again, this takes just a moment. And then I again reduce it through the ideal, the remainder comes out 0. And that's it. And I'll go back to the, you guys see the slideshow again?
Yes, no problem.
Excellent. I hope I didn't go through that too quickly. The big deal is you can show that TW is an integer and that it is in fact in the kernel of this operator. That's the deep thing. Now, from then on, the proof of the actual theorem is not that hard to do. Again, this should be V6. I beg your pardon for that. Otherwise, it's a pretty standard proof that if L1 is in the set that we want, then we can show for any L alpha, for any odd index L alpha, we can go to L2 alpha, and it gives us the property we want. It's going to be in V5 and 0. I've got the power of 5 that I need and applying the U operator. And then going the other way, I don't even need any additional power of 5 at all. So it's pretty straightforward to prove from that point on. And that is the walkthrough I wanted to give you. So the big thing to point out is taking into account the topological properties of the Riemann surface, we can construct very precise kinds of representations of the associated generating functions. We have to take into account this interesting operator. I call this the congruence operator, and the kernel of it's the congruence kernel. That's sort of the really key idea to proving this. If I have a congruence family like this here, say, and I'm working over x0L, the modular functions over gamma 0L, L is a prime, and say the genus is 0 just for simplicity's sake right now, then I know I can write alpha basically like this. As some polynomial and a given x, and strictly speaking, the functions S are in a kernel of an operator, but in this case, the operator is very, very, very trivial. It just sends it's just the 0 operator. So everything's in the kernel. That's why you don't have to worry about this. That's why you don't even think about this when you do these standard proofs. When we're working over X0 to L, again, I'll say genus 0, although again, it doesn't change if you change the genus. I mean, it changes a little bit, but the key ideas don't change. Instead of L alpha just being a polynomial X, it's a rational polynomial. Z is a polynomial on X as well. Rigged properly so that it's not divisible by the prime we're worried about. And now SM is going to be in the kernel of some linear operator omega that can be fairly easily expressed. Although showing stability and so on is a bit tricky, it's not that bad. Okay, and the one I just showed you is a good example. All right, working over X0 4L. These are some of the more difficult congruence families. In fact, some of the hardest ones. We have proofs of some of them. For Andrew Sellers is a very good example. The Andrew Sellers partition congruences. They've been proved, mind you, but I'm not very satisfied with the proof myself. The proof works, but it doesn't have the associated algebraic structure is not obvious. It comes from a lot of guessing and a lot of experiment, a lot of ingenious experimentation, but it's not obvious. I would like a proof like this here. It's not so easy to get because this linear operator it exists, but it cannot easily be expressed. And I won't get into how to express omega because I'm still working on it, and I'll tell you about it maybe a little later if I can figure a bit more out. But that's basically the key idea. That's how you can classify these congruence families. It's not just the genus. The genus has a fairly straightforward effect. The cusp count, I think, has the next really important effect. X0 4L, you have more cusps, and that complicates things, and it has an effect on this kernel here. And that is the key way that you can classify these. Whether in a sense the level is prime, 2 times a prime, 4 times a prime. And there are other ways, there are other congruence families where it's not just a power of 2 times a prime. That seems to be the most straightforward way to start talking about it. And actually, I'm not that early. I got about 10 minutes left. So I think that's a good stopping point. So I'll stop there. That was what I've been working on the last couple of years. Thank you, guys.
Thank you, Nicholas, for a very nice talk. Any questions?
Hi, Nicholas.
Yes.
Yeah, thank you for your very interesting talk and wonderful work. I have 2 questions.
Please.
Can you hear me? Yeah. The first question is how do you analyze the poles of the function z to the powers of m times L alpha in the first few pages, I think.
So you go back here a bit.
Yeah, in the first, maybe I don't remember.
It is here?
Yeah. I think in this place. Yeah, because L alpha is defined recursively. So how do you locate its poles? Because you said it's.
Well, see, you can start out. Say, look at L1 as an example. Usually that's the base case. You can look at that, and then you can look at how the U operator is going to affect the poles. That's not so bad. So really, if you look at the base case, say L1, you're usually set. And if I look at, for example, L1 looks like this here. Don't worry about all this, but it's D5 with 5n plus 4. And if you're familiar with Ramanujan-Kohlberg type identities, we can rig this so this is a modular function. And in fact, we have formulas. My colleague Sylvia Radu has formulas, for example, that will estimate the poles for L1, or estimate more of the order of L1 at the associated cusps of the modular curve, like lower bounds. So you can figure out where L1 is likely to have a pole and where it's not likely to have a pole. Like where it won't have a pole at all and where it does. So that's the first step. Let me go back here again. So you can figure out where L alpha can possibly have poles. And I can build a function Z that, and not only have poles, but I can put lower bounds on the orders. So maybe it has order -2. I know it will probably have order -2. It won't have order -3 or -4. So that puts a limit on how serious the pole order is going to be. And I can build a ZM, an eta quotient, that is guaranteed to kill the poles everywhere except, say, 0. That's easy to do. We can build an eta quotient. I can go even further. I can tell you it's an eta quotient, at least over gamma 0 n. Also using some of the, not even Sylvie Radu's computation, I think some of Neumann's computations from decades ago. You can build an eta quotient with positive order, all the cusps except for 1, say 0. And that will guarantee when you, and since you can estimate the order of L alpha at all its possible poles, you can figure out how high to raise this power m to kill the poles. So that's actually a lot easier than you might expect. It's a little trickier getting Z and X in just the right form so that the divisibility comes out the way you want it, although even that's not that bad. For example, if the genus is 0, you can just say, you can often just write Z as your Haupt module. So Z to the m times L alpha is a polynomial in Z. And you would expect just to write L alpha as just a polynomial in Z and 1 over Z. That doesn't work, usually. You don't get the divisibility properties you want. So usually you have to rig Z and X in just the right way. But even that's not that hard. But the pole issue is not an issue at all. You can build an eta quotient that easily kills the poles of L alpha, and you can estimate the poles of L alpha.
Okay, yeah, you remind me something. So you say that it is hard to decide the exact order of the poles, but you can give a normal estimate for it, and that will suffice for this problem, right?
Oh, yeah. In fact, I wouldn't be surprised if there was a formula for getting the exact order, but we don't need it. I'm not familiar with one, but there might be one.
Yeah, we only know some estimates for the normal bound after the U operator.
Yeah, exactly.
Yeah. Okay.
And
yeah, you go. You say first.
no, that's it. That was it. Please go on.
Yeah, my second question is about the exact order of the prime that divides the partition function. I mean, you know, in some partition functions, I think the power of the prime can be increased when you restrict to some higher order sequence. So please go to the page with your theorem with the theorem on the D5. Yeah. For this congruence, if we allow alpha to start from some natural number, for example, alpha is greater than or equal to 3 or 5, maybe we can improve the power of the 5, right?
It's possible. I'm not sure. Usually I work with just the first few small cases. I have some algorithmic procedures for working with larger cases to try and optimize these powers. That's what you're talking about, right? So optimize them. Maybe for a larger alpha, this is a bit higher.
Yeah, right. This is my question. How to optimize the choice of this power?
So in my experience, the best thing to do is to actually do some computations. But so for example, George and Peter did a similar congruence family to this for powers of 3 as D2 of n. And they said, I think when 8n is divisible is 1 mod 3 to the alpha, then D2 of n is divisible by 3 to the alpha. And 3 to the alpha is not the optimal result. But the way I got it was just by doing some experiments on the first few cases. There's also an algorithm that I developed with Sylvie Radu that allows you to check a congruence family for several powers of alpha. You can prove maybe the first 10 cases, which if you think about it, is very hard to do computationally. But we rigged it so we can in fact check, say, the first 10 or 12 cases fairly quickly on a computer. And you can look at the maximum power of the prime dividing your, in this case, D5 of n. So we have some computational procedures that can check beyond even the first initial cases. And that's usually how I do it. The other thing is this manipulation with this linear operator, this congruence operator, suggests that these congruence families are a little delicate, that they have to satisfy certain very precise properties to gain a power of 5 at all. So I would guess, and I might be wrong here, I might well be wrong, and I'd be interested if I were, I would guess this is optimal, even for large powers of alpha, because it looks like it's very delicate going from L alpha plus 1 to L alpha plus 2. And if you don't have exactly the right form, it won't gain the power of 5. So I would guess this is actually optimal, though maybe I'm wrong. I'd be interested to know if I were.
If you start with alpha equals to 1, then I think this is optimal. Why do I ask this question? It is because in my previous work on 6, 3 and 9 colored Frobenius partitions, I actually improved some similar congruences of Cornish, but the restriction for the alpha is I need alpha to be greater than or equal to 4 or 5, I think. So it is a partial. It only improves the power when alpha is larger, but not starting from the first case, from the initial case.
That's interesting. That's very interesting.
But I think your congruence is optimal if you because you are not this congruence is suitable for every alpha, not only for the larger alpha.
I think it is. I think it's optimal as it gets, although I'm not certain. And I've got methods of testing it and checking whether the divisibility gets greater as you go on up. But it would be very interesting to know. Like the thing is, again, this may have some connections to the level of the associated congruence family. Do you know what the associated modular functions were that you were working on there? Like, was it gamma 0.6 or gamma 0.9 or?
Yeah, gamma 0.9, I think.
It was gamma 0.9.
Yeah.
Very. And it was an infinite congruence family.
Yes.
That is interesting.
Maybe I should double check my paper because it was written a long time ago.
Actually, I would be very interested if you showed me that paper. The reason is I've actually been trying to search for congruence families. And most of the ones I find, the infinite ones, like of this form, happen when it's x0 of the prime you want, multiplied usually by a power of 2. There were 1 or 2 exceptions to this, but they're not common. But maybe I just wasn't looking properly. I'm very eager to find other infinite congruence families. And again, I'm working on classifying them. So if you found one where it, for example, it's L squared and L's odd, that is very interesting to me. And that means that my classification procedure is not perfect. And I'd like to know that.
Okay, I will send you my paper and the paper of Cornish.
Thank you very much.
Well, thank you. That's all of my questions. Thank you.
Any other questions? If not, let's unmute ourselves and clap.